Hello dear viewers, Assalamu alaikum. In our last lecture, we studied how to control our flow using pump with the help of manual and PID control mode. Today we will discuss what is PID controller and why do we need it and how to use it. So let's start with a little recall of our last video lecture. In our last lecture, we used this PCU simulation software, which stands for Program Control Unit Simulation Software, where we had to control our flow control of the pump using manual and control mode. So let's recall that here is a set point value. Set point is the value upon which we need our pump to work, and we required our liter per minute, such as 1.2 liter per minute is required. This is MV measured value, which is pump, and the output which we are receiving at our output in the form of liters per minute. So basically this PID control mode works on the basis of the difference between these two values, set point and the minus measured value, and the result will then work on the PID control mode to automatically control the value and bring the output value up to this set point. So let's start. What is PID controller? A PID controller is also called proportional integral derivative controller as it is explained through its PID controller PID name. Proportional P stands for proportional, I stands for integral, and D stands for derivative control mode. It is also called three-term controller, which is used to collect some input data and function it through using different modules and then output it. So this is a completely circular loop system. This PID control works on the loop system. It take value, process it, and give it output. Then again at the input, it take that feedback value, and again it will produce your output value by minimizing the error. So let's read this paragraph. A proportional integral derivative controller or three-term controller is a control loop mechanism employing feedback that is widely used in industrial control system and a variety of other applications requiring continuously modulated control. In practical terms, it automatically applies accurate and responsive correction to a control function. So PID controller basically works on just simple one value. It will process it, and by reducing the error, it will give you the output. So a PID controller continuously calculates an error value as the difference between a desired set point, which is our set point value, and a measured process value, which is MV, and implies a correction based on proportional, integral, and derivative terms, as these are denoted by its name. Let we explain this PID control with the help of an example application. The application is an everyday example is the cruise control on a car. You people already know what is cruise control in the cars. Cruise control is the option, for example, if you are going on a long route and you want your car to maintain the speed at 80 miles per hour or 80 to 90 kilometers per hour. So you just simply click that cruise button and your car will automatically sustain that value. Now, for example, you are going on a hilly area in ascending direction or something else, and you have just simply clicked on this cruise button. So that cruise button will only fix that value of accelerator to the 80 kilometer per hour. If you are going on a hilly area or a steep hill in ascending direction, so your car will require more power. That 80 kilometer per hour does not work in that situation. You have to accelerate more your value. So that simple thing will automatically controlled by your PID controller. Or for example, you are going in descending direction, okay, and in that position your car will achieve automatically more speed simply on that 80 kilometer per hour. So in that direction, so in that descending direction from the hill, you will have to reduce the speed of your car. So that reduction in accelerator will automatically controlled by your PID controller in that situation. Example of this is automatic steering system in the ships which were developed in 1920s. So this PID control was developed in 1920s to control the automatic steering system of the ships. For example, you have to turn your ship in the direction of north 20 degrees, okay? Velocity due to the resistance of air and due to the impact of waves, your ship continuously change the direction of that. So you can simply control automatically that shared direction using PID controller. Okay. Now let's try to understand that situation with the help of this this feedback loop system. Now here this R with respect to time is our basic function. Here we can say that this is our desired or required value. In our case, as we recall our last lecture, we have to set our 1.4 or 1.5 liters per minute value. So for example, this is the value of 100. Let's say this is 100 value. It will then comes as a e with respect to time. This is stands for error. Now error is a set point minus measured value. So this error will first iterated through this proportional value by multiplying with this coefficient factor, which is stands for k. Kp is the proportional constant factor. It will multiply with this error value, then it will go to the integrated value, where it will further iterated through integration, and it will reduce the error. And then after that, derivative function, that same value, that same sp minus me value will first iterated through proportional, then it will go to the I value, and it will go to the derivative function. Or it can continuously go at any mode with depending upon the error value. And at the end, we can collect sum of these all modes, and it will provide us our output value. Okay. At our exactly achieved output value, we have another feedback system, which will again help to create another error. It will be reduced. For example, you have 100 value over here, and here you can get 80 liters per minute, let's say. So this 80 will again come back to this feedback system. It will then multiplied or add or subtract with this value, and now this condition et will be as 20. So this kp will Kp, Ki, and Kd will act as coefficient factor, which will change the value of this error with respect to time, and it will again. So for example, in second iteration, you have received out of 100, you are receiving here, let's say 92 liters per minute. Again, this value will get back over here. It will then be processed by these three modules, and then at the end, maybe after 5 or 6 or 8 iterations, you can achieve 100 value over here. Okay. Now we will discuss what is this proportional, integrative, and derivative mode. So term P stands for proportional to the current value of the set point minus processed value or measured value. This SP minus PV stands for set point and processed value or measured value, the value which we are receiving at the end. And this E with respect to time stands for error, this value with respect to time. So this P is proportional mode, which acts only when there is difference. For example, your set point is 100 and your achieved value is 80. So there is a difference between these two values is 20. If both of the values is 100, so this proportional value will become 0, and it won't work in that situation. Okay, because there is no error and there is no difference. So this is called set point. Okay, this is called our proportional module. Now this won't work in that situation where our output value becomes more than this. So in that situation, this proportional, the difference will become in negative value. So that value will have to become reverse. So in that situation, it will not work. Then at that point, our integral mode will come in action. Now, what is term I accounts for past values of the SP minus PV error and integrates them over time to produce the item. Now, that value which was proportional SP minus PV will come in this integrated mode, and it will integrate. After integration with respect to time, we can get our item. For example, if there is a residual SP minus PV error after the application of proportional control, the integral term seeks to eliminate the residual error by adding a control effect due to the historic cumulative value of the error. When the error in this integrative mode, this value, this big difference will become iterated many times through this integral module, and at the end, such as oscillating behavior or such as the spring and damper behavior, it will reduce to the desired output. This derivative mode does not work to reduce the error. It does not try to reduce the error from 100 to from 0 to 100 or whatever. It will just control the error rate of this integration module. The term d, this derivative module, is used to control the term rate of the error rate of this integration module with respect to time. Okay, so I have also created a short video lecture which will easily understand what are these things and how can you understand this. Now this is tuning. Tuning is just showing you that the tuning is just meant by how to control how this complete loop system is controlling your main output, such as control of the valve from 60 to 70% or 80 to 90%, or controlling of the thermostat at the output just to achieve our required temperature using this PID control. And this control action is used where you need, where you sometimes needs the opposite of that situation. For example, you have to control you have to increase the flow rate of the water, but in some cases you also need to decrease the flow rate of that pump. So in that situation you have to change your control action. Now let's go to the mathematical form. The mathematical form is this, where u with respect to time is the overall function, and et, this et is that error value which is the difference of set point minus measured value, and this kp is the coefficient of proportion which we have achieved after first iteration. This ki is the coefficient of integration, and that same value is then integrated with respect to time. That t dash is the time domain, and in derivative, that same error e with respect to time is derivative with respect to proportion of the constant of proportion of derivative. Okay, so this was our use, and here we have discussed few limitations of this proportional, integral, and derivative modules. So let's go to our video lecture and we can easily understand what we have studied so far. Now in this PCU simulation software, we have two modes: control mode using PID, and another is manual control. This PB or PG is showing us direct proportional, which is P. PB is showing us 100%, which is means you have to reduce error 100% using proportional module. This I stands for integral mode and D stands for derivative mode. Okay, this is set point. Set point is the value upon which you want your pump to work, such as for example I want my pump to work to produce 1.5 liters per minute. Okay, and this is measured value. So let's start. Now here I have start this video without using any of these operations. Shows us that our set point value is 1.5 liter per minute, and our measured value is around 0.7 liters per minute, showing in these two graphs. Now we will go to the proportional plus integrated mode and start the video and start the simulation. Now now you can easily understand that how that integrated values are applying on this. For example, at the first, pump was working more than the required value, and then after first iteration it reduced the value. After second iteration it more reduced, and simply is showing us the oscillation behavior, and with respect to time, that simply iteration process is reducing the error, and we can achieve our set point value. Now let's go to third point, using all of the three modules. Now this, let we clearly understand that this derivative module does not does not help, does not try to reduce that error, but it work on this oscillational behavior of integration. It work on the behavior of this integration with respect to time to achieve our desired value in minimum work, and also to bypass that adverse effect. Now you can easily understand that this we have achieved our value in very small time. These three values, 100, 0.2 and 0.3, are the values of kp, ki and kd, which you can easily change and you can check the behavior of this value. Thank you very much, guys. I hope you have understand the video lecture, and if you have any questions, you can simply ask in the comment section. Thank you.